Okay, from the last quiz, here's questions 6 and 7, where we are titrating 25 milliliters of 0.2 molar propionic acid. I'll call that HA, which has a Ka of 1.3 times 10 to the minus 5, with 0.1 milliliter NaOH. And the questions are, what's the pH after 40 milliliters of base added? That's question 6. Question 7, what's the pH after 50 milliliters of base added? Okay, and I started with information we need to know. If I have 25 milliliters of 0.2 molar acid, I know 0.2 millimoles per milliliter, that's molarity, times 25 milliliters, milliliters canceled, and we've got 5.0 millimoles of HA. Now, the reaction that's going to occur when you add the sodium hydroxide is HA, the acid, plus the hydroxide, is going to react to form water plus the conjugate base A minus. And since this is strong base weak acid, we know this is a 100% reaction, so I need ICF for my table down here. And recall these need to be in units of moles or millimoles. So I know that I've got 5.0 millimoles of HA to begin with. I'm not worried about water, and I don't have any A minus to begin with. And so how much OH, how many millimoles of OH do we start with? Well, it's 0.100 molar, which is 0.100 millimoles per milliliter, times my 40 milliliters equals 4.0 millimoles of base. So I know I've got 4.0 millimoles of base there. And then this is just limiting reagent. Well, 5 millimoles, 4 millimoles. The 4 millimoles is my limiting reagent. So subtract the limiting reagent amount, but on the product I have to add that amount to the product side. So I got 1 millimole of HA left over, no OH minus, and I've got 4.0 millimoles of A minus. Well, I realize if I have HA and I have A minus, then this is a buffer solution. And that means Henderson-Hasselbalch. pH equals pKa plus the log of the base form divided by the acid form. And normally this would be in concentration, but we know since it's all in one solution that the molarities will keep, the volumes cancel out, so I can just plug in my moles. pH equals pKa, which is the negative log of 1.3 times 10 to the minus 5. That is 4.89. Plus log of A minus, 4 over HA1. Plug this in, and I find that the pH will equal 5.49. Take the log of 4, add that to 4.89, you get 5.49, and that is the answer to question 6. All right, question 7, a little bit more involved because now I'm adding 50 milliliters of my base. But I start with this ICF type table here, H2O plus A minus, because here's my reaction that goes 100%. Initial change final. And recall my initial amount of HA is still the same, 5.0 millimoles. I'm not going to worry about the water at all. And what else? Okay, I need how much base I was at. Well, 50 milliliters times 0.100 millimoles per milliliter. Milliliters cancel, is 5.0 millimoles. Okay, so that means my amount of base is also 5.0. I don't have any A minus to start with. Note, it's the same amount. We've reached the equivalence point, so we've got no HA left, no OH minus left, because we have 5 millimoles of OH minus, 5 millimoles of HA, and then that gives us 5 millimoles plus 5 here, 5 millimoles of A minus. Well, which means at this point we've got A minus in water, but what is A minus? Well, A minus is the conjugate base of HA. HA is a weak acid, has a Ka value, so HA is a weak acid. This is a conjugate base of a weak acid, which is a weak base. So I know this is a weak base in water, so any weak base in water will be an equilibrium reaction with HA plus OH minus. That's why it's a weak base, because when you add it to water, you generate hydroxide. Since this is equilibrium, this is now a good old-fashioned ice table. And, oh, but remember, ice tables need to be in units of molarity. So I need my molarity of A minus. Well, concentration of A minus is 5.0 millimoles divided by the number of milliliters. Note, I added 50 milliliters of base, but I started with 25 milliliters of acid, so this is 75.00 milliliters here. And do some quick math. This is 0.0667 molar. So my concentration of A minus 0.0667. Water we're not going to care about. No HA before this dissociation, no H minus before the dissociation. The change, this is ice table, minus X, and plus X. 0.0667 minus X, and X. And then we have to realize, okay, so we need to plug this into the equation here. But we've got a problem in that this is the conjugate base. This is A minus, the conjugate base of the acid. So we need the Kb value here. We recall that Ka times Kb equals Kw. Therefore, the Kb value will equal Kw divided by the Ka. So Kw, 1.0 times 10 to the minus 14th, divided by Ka, 1.3 times 10 to the minus 5. When we find Kb equals, what does that equal? Kb equals 7.69, 7.7 times 10 to the minus 10. So now I plug that in because Kb will equal the concentration of A minus times concentration of OH minus divided by the concentration of HA. 7.69 times 10 to the minus 10th equals, well, A minus and, HA. HA, and this is A minus down here, because HA and OH, A minus down here. HA is X, OH is X, so that is X squared over 0.0667 minus X. Can we get rid of this minus X? 10 minus 10th? Sure, so let's just, don't worry about that minus X. Take 7.69 times 10 to the minus 10th, multiply by 0.0667, square root your answer, and you find X equals 7.16 times 10 to the minus 6. Well, that's our concentration of OH minus, so it's in terms of molarity, units of molarity, and that X is our concentration of OH minus. Now we're after the pH, but I know if I take the pOH, which is the negative log of the concentration of OH minus, negative log of 7.16 times 10 to the minus 6, I find the pOH equals 5.15, and I know pH plus pOH equals 14.00 pKw, and therefore I can calculate my pH to be 8.85. So there you go, question 6 and 7 on the quiz.